Oops.
And now everybody's busy right now. Gina's also.
It's streaming. We're live.
Good evening, everyone. If I may have your attention, welcome to the January meeting of the Madison Astronomical Society. And it still sounds like that signal's a little bit hot. Is that hot on your end? Is there too much signal for the voice? Because I'm getting some ringy feedback stuff.
It seems okay. Yeah, that's before it gets to this. So
All right,
that's.
bear with me, I'm gonna turn down the master fader a bit. I'll be right back. Hopefully this works better. We're getting some fun feedback earlier. The master fader is the main dial that turns down everything in your power mixer. That's what they call a fader. Not a euphemism. It's a sound nerd term. All right. I'd like to welcome everyone to the January meeting of the Madison Astronomical Society. A lot of fun stuff's been going on, and I don't know if I see Jack here. First of all, I'd like to thank the entire group of people that we have working on the newsletter, and we had an amazing relaunch of the newsletter last month. Jack, would you like to say any words of thanks to all the people that helped?
Well, I'm grateful to all the people who contributed. I'm happy to say that we're suffering under an embarrassment of riches. We had a meeting the other day, and there's a terrific number of people who are interested in writing. So I think we're gonna have a larger issue. Someone on the team said, maybe we should call it a magazine, and I said, maybe you should find a new editor. But, in any case, we have a lot of work ahead of us, but I think it went real well for the first time. So to all who wrote and enjoyed, thanks.
Thank you very much, Jack. Yeah, we're very much looking forward to the next issue. It sounds great. There's been also a lot of volunteer work over the last year over at YRS, and it's impossible for me to thank everyone that's been involved, but it's just been an amazing year of participation, and I just look forward to all the people who are just showing more enthusiasm for the Honor Research Station and the club, including the newsletters. So it's looking like it's going to be a really great year this year. While I have Jack, Jack brought up an interesting bit of information that if for those of us who belong to the Astronomical League, there is also a regional club that has some meetings and benefits and a newsletter. So if you saw the email newsletter, the email announcements that I sent out last weekend, there's a URL in there that if you want to sign up for the league's North Central region, also referred to as NCRAL, or do they call it NECRAL or something like that? If you want to sign up for their quarterly newsletter called Northern Lights, there's that URL that I provided in the email, and you can sign up for that as well. So look out for that. Did you want to say anything more about that, Jack? Or is that okay? All right. Coming up next month, right here at UW Space Place, Friday, February 14th, our next meeting at 7 o'clock will be a guest presentation titled My Solar Astronomy Journey, a special presentation by astrophotographer Brian Champion. And those of you were fortunate enough to be here the last time Brian gave a presentation about how he built his backyard observatory. He's going to give a presentation about his interest in solar astronomy, and he wrote about it. My interest in solar astronomy started when I got the opportunity to look through a solar hydrogen alpha telescope in the 2017 eclipse. I was captivated by what I could see on the sun. So in this discussion, I'll go through how I started my solar astronomy journey, equipment I've used, and the things I've tried, and the custom equipment I built, and the equipment I'm currently using, and the processing techniques I've learned to create dramatic, high-resolution solar mosaic images. So for those of you who are active on our Facebook group, Brian has posted a lot of really great solar images on there. So next month's meeting is going to be a really a good opportunity to learn more about solar photography. So keep that in mind. Coming up here at UW Space Place next month, or this next week, I mean, Jim Lattis, Dr. Jim Lattis is going to be giving a presentation right here at this very same venue this Tuesday at 7 o'clock called What's Happening in the Sky During 2025. I think the title says it all. I thought I saw Jim here a little while ago. I don't know if he wants to say anything about his presentation, but I don't see him at the moment. Further off into the future, save the date, Saturday, April 5th. You know you need unique New York, for those of you who have ever been in theater geeks type stuff. Saturday, April 5th, 2025, at 5 o'clock, we are having our 90th anniversary gala celebration and the return of the MAS banquet. And we are being hosted in a very lovely building on the grounds of Promega Corporation. And we've got some very lovely catering that we're trying to line up. And for those of you who are there during cocktail hour, it'll be an opportunity to see the observatory that Madison Astronomical Society used to call home. It used to be called the Oscar Mayer Observatory, and now it's called the Bell Burnham Observatory, named in honor of the woman who was key to discovering pulsars way back when. So it's going to be a really great time and a fun time to hang out with some friends and also maybe see some people who used to be members of the club a long time ago. So save that date. Yes, Jack, do you want to say some additional information?
One thing, I don't think I need the mic. We are gonna sell tickets beginning at the next meeting. Our next meeting, MAS meeting, is February 14th. So we'll be selling tickets here. And the only reminder is, it's for members and a guest, but make sure your membership is up to date. But
Yeah.
we'll be selling tickets, they're $35 a plate, and they'll go on sale starting the 14th, and then afterwards, we'll send an email out with a registration form if you'd like to do it that way.
So, yeah, Jack was just telling everyone, starting at the next February meeting, they'll be selling tickets for MAS members only, plus a guest for $35 per person for this gala event coming up in April on, I lost the date and I forgot it already, April 5th on Saturday. Yes, Jürgen.
Yeah, I just want to make the point that I believe everybody here is honest, but I do want to say that these are family memberships. So if you sign up and you have 3 members of your family, not everyone gets to come. Only 1 person per membership can buy the tickets. So if you have a husband and wife, the husband can't bring a second, and the wife cannot bring a second.
Yeah, space is going to be kind of
A
limited.
little bit, but I just want to point that
And
out.
for those of you who remember when we used to have the banquet, we used to have an almost large enough venue for it, and there'd be 45 of us, and we'd be elbow to elbow. So we should be doing better on space this time, but yeah, space will be limited for this. Does anybody have any questions about the gala banquet? All today, all right. I will look through my notes and see, oh yes, coming up this month from January 22nd through January 23rd. And I heard somebody, a member earlier, saying that they really enjoyed the event that they just recently saw at the planetarium at the Madison Metropolitan School District. The high school there, the Memorial High School on the west side. They have a presentation coming up this month called The Dying of the Light, We Hope. The program goes like this. Join us as we explore the differences between effective lighting and light pollution. Learn more about how we can work to protect human health, wildlife reproduction, ecology, public safety, and reduce energy consumption and its cost on the carbon footprint. We will explore the mounting knowledge base regarding artificial light at night and a very modern problem, light pollution from satellites in space. So they've got 2 presentations on that Wednesday and 2 presentations on that Thursday. January 22nd, 23rd, at either 6 p.m. or 7:30 p.m. $6 per person for Madison City residents, and tickets can be purchased in advance on their website. And I also wanted to give another quick word that just to remind everyone, for people who are newer members of this club, there is an opportunity to interact with astrophotographers from the Milwaukee Astronomical Society, the other MAS. They have a monthly meeting that they have hosted online. I forget which, if they use Zoom or some other thing, but if you look back at the email blast I sent out last weekend, we can contact Matt Rhino and they can set you up if you would like to join that astrophotographers, what I like to call a jam session, because people literally just show, work together and chat together or give presentations on how to do astrophotography better. And they also have a Slack space set up, so if you're out by your telescope trying to take pictures and you're having a technical issue with PhD guiding software or something, you can get on Slack and ask somebody a question about PhD and you'll probably get a response pretty quick. So that's another benefit with joining the Wisconsin Imagers group. All right, I think those are all the announcements I had. I just wanted to take a little moment to ask if there's anybody here that has not attended a Madison Astronomical Society meeting before, if they would like to introduce themselves. I will be right with you. Oop, sorry about that.
Let's just move that chair.
Oops, sorry.
I'll move that chair.
Yes, what's your name?
I'm Jordan Marche. I live in the town of Oregon. I'm retired a few years ago from teaching astronomy at UW-Madison, a lecturer in the department, so I do have a pretty broad background that way. And I think it's about time I find out more about your organization.
It's really great to have you, because our club was founded by a member of the faculty, was one of the founding members of the faculty, and it's great, and we have other faculty members and alumni here from the university as well, so.
Plus, you're on the right side of the town to go to our dark sky site.
Yes. It's a pleasure to meet you. Is there someone else that would like to, oh yes, I'll be right with you.
I'm Samyak. I'm a new grad student at the university. I was just looking for people who like stargazing, and then I found this Facebook page, so here I am.
Well, that sounds really great. It's nice to meet you. And there is also, at the university, does have an astronomy club. I'm sure there's some way to search all the various clubs for university students, but you might be able to hook up with them as well. All right, it's a pleasure meeting everyone. And I guess we're getting close to 7:30. Kevin, would you like to introduce tonight's guest speaker?
Absolutely.
I'll hit pause. I'll hit pause, but that's my phone, not the.
Okay. All right. Our guest speaker tonight is Bob Hamers. For most of you in this room, no introduction for Bob is really necessary because he's been a long-term member of MAS. And a lot of us from Astronomical for doing astrophotography have used him as a resource. He's been a great friend to a lot of the astrophotographers in this group. If you visit the MAS Facebook page often, you're undoubtedly familiar with some of Bob's work in astrophotography, including solar, lunar, and deep sky objects. He's also has some amazing video of near-Earth asteroids going by. How we got that, I'll never know. Okay. Bob is a UW-Madison professor of chemistry. His UW research centers on chemical and structural analysis of solids and their surfaces. And I personally find his knowledge and research into promising properties of nanoparticles and various nanostructures kind of fascinating. I'm thinking that sometime in the future we're going to see feature movie about how Bob netted together some nanotubes to save Earth from passing asteroids. I just want screenplay credit for that, Bob. Okay.
He's filming them as they go by.
Yeah, exactly. Exactly. So that said, I want to introduce Bob Hammers.
Okay, thank you. Okay, is this hopefully on?
Yes, it is.
Okay, let's see here. Here's my little clicker. Okay, a little fancy pointer that lets me actually use a pointer. We're not up on the screen.
The screen might have gone to sleep on the projector. Or maybe not, yeah, the projector's on.
Do I need to do something?
Do you need a pointer? I happen to have a pointer.
No, I mean, that, actually, this actually works really well, but my computer's not showing up here. Here, let me just unplug this and plug it back in.
Was it showing previously?
It should have been, I turned the projector on a while ago and it looks like the projector's on. Maybe it's the input. Source search, USB.
Turn the feeder down too far.
You were seeing it on your feed, right?
Oh, yeah, I was, that's right.
Are you seeing it now?
Let me check. Yes, it's on my feed, so it's the projector.
Oh, yeah, now it's back on now. It's showing. Yep.
It's blinking.
There we go. Oh, yeah. Maybe.
I turned it on, there we go. Sorry.
Okay.
There you go.
It'll come up a little brighter than that.
We'll turn a couple lights off.
All right, the little pointer works.
Oh, I always guess the wrong one.
Yeah, okay, all right, well, thanks very much, pleasure to be here as always. I'll tell you a little bit about today, about some of the work I've been doing over the last 6 or 9 months, focusing on lunar and solar image processing, and kind of going into some of the details of the image processing, and I'll talk about the goal in just a minute, but, all right, so Kevin mentioned that I'm a UW professor of chemistry, and people wondered, well, what does chemistry have to do with image processing? So I thought I would simply bring up that actually I've been doing image processing since about 1985. Okay. Shortly after I got my PhD, I got a job at IBM just north of New York City, and was working on a newly developed kind of microscope called the scanning tunneling microscope that was inherently digital. So this is actually the microscope, that's me, all right? Here's the microscope, but the important thing is the images were completely acquired digitally. There's no photography, anything acquired digitally. And this is an example of one of the images that I took back in 1986. And these are atoms, right? Every round object there is an atom. And you wonder, well, what's chemistry got to do with it? Well, you see there's two kinds of atoms there. Some of those atoms are silicon, some of those atoms are aluminum. And so the idea that microscopy can give us information about chemically what's happening in materials turns out to be very important. And at this point in time, 1985, Photoshop didn't exist. So pretty much the image processing had to be done basically by writing computer programs in Fortran or other languages back then. You know, the more things change, the more they stay the same. One of the issues with those early images was that they're often highly distorted. So this image, for example, also from 1986, this should have been a square. But this microscope had a lot of distortions to it, and so we had to develop software that would do these kinds of corrections. So there are things like calibration, image distortion, things that are very similar to the things that we do with astronomical images. The main difference was that, of course, there's a lot more software available, the images are much bigger, the expectations are much higher, but it also brings a little bit of a mindset that when I think about astrophotography, I'm thinking about the artistic part of it, but I'm also thinking about it as a scientist would. I'm thinking about it as being scientific data, and I kind of bring that mindset to what I do. So with that in mind, in 2024, there was this interesting article in Scientific American about colors of the moon. Now, as somebody who studies solids, I know that the color of an object tells you something about its chemistry, and I was very much intrigued by the fact that these accentuated color images have regions of different colors. So this image area that's a little bit more blue, for example, has a high concentration of titanium, titania, TiO2. The regions that are brown tend to have more aluminosilicates. There's regions that are more yellow. Now this is very much accentuated, but I just got really interested in this. And around the same time, I had taken delivery of a brand new full frame imaging camera, 16 bits, 9,000 by 6,000 pixels. And I thought, you know, I really want to take a high resolution image of the moon in color that is large enough that I can actually make a poster like the ones on the wall that are 2 feet in size, where the resolution is such that you can go with a magnifying glass and see that the image is sharp at the limit of identification. Okay? So I did that, and John Rummel got really excited when he saw the image I took of the first quarter moon, and he struck up a deal that if I gave him data, he would make a print on metal, which is what you see on the chair. And then I've also continued and done a third quarter moon, which isn't quite as good, but that's posted on the wall, and used some of these same methods to do a solar image, like a continuum image that's there. But the trick is like focusing on the idea of really making use of the full resolution of your optical system and the camera and all the processing to be able to go and make really high resolution images that are poster size. Okay, so my rig is not too much different from what many people in this society have. It's a 5-inch refractor. I use a 1.5 extender, so I've got about a 1,300 millimeter focal length. I've got a 2-inch filter wheel, and then again this full frame camera that's got a nice big area and many pixels, and then it's just on a standard mount in my backyard. Okay, so nothing too special there. Now, for those of you who haven't done this kind of imaging before, when you're imaging planets, things that are extended in size like the sun and the moon and the planets, you're in a regime where you're doing what's called lucky imaging. And the basic problem in imaging these extended objects comes from atmospheric turbulence and the fact that, as you'll see, these images shimmy back and forth, they come in and out of focus, and so you kind of get lucky. What you do is you take many, many images, and then you sort through and find the sharpest images and the sharpest parts of the sharpest images in order to reconstruct one really sharp image. So the basic flow is here. We'll kind of go through that. But as a starting point, you want to kind of set up the optical system to maximize the collection. You can kind of work through like what's the resolution of your eye. If it's 18 inches away from something, you can see things that are about 200 dots per inch. So if you want to make a poster that is maybe 18 inches, or the big one there is about 24 inches tall, you want something that's got something like 3,600 by 3,600 pixels. So if I take Stellarium and put the moon in there with my telescope and my camera, here you can see the field of view, and this is about 6,000 pixels in this direction. So, this is a pretty good match to about what I would want. Okay? Some of the challenges of doing this, like this is a really nice camera, but 16 bits and 9,000 by 6,000 pixels mean every image is like 100 megabytes. So if you take many, many images, there's a challenge associated with handling the data. But anyway, we'll get into that. Today I'm going to talk about two candidates. We'll spend most of the time talking about making the moon image, this one, a little bit greater than first quarter moon, which led to the image that's on the chair there that John provided to me in metal. But the same techniques that I'm going to talk about also work for solar imaging, so I'll show you a couple examples for that. That actually highlights some things that are difficult to see in the lunar imaging. And I think this should also work on planetary imaging, although I haven't gone back and reprocessed some of my data there. But in particular, the devil is in the details on this, and so you see an image like this and you say, this looks great, but what you really want to do is go and look at it under a magnifying glass and really pixel peek, right? And say, is it sharp at the limit of the single pixel level? That's my goal. So in order to do that, as I go through today, I'm going to highlight expanded regions in a couple places. So in the sun, I'm going to focus on this little region right here. It just has some kind of nice structure that I can work from. And on the moon, I'm going to work from two regions. One is this crater called Clavius down here. Clavius is nice because it's got a whole series of craters of different size, so it's kind of nice to kind of compare that. And it's got a lot of structure. But I'm also interested in making sure that we can handle the regions where there's very little contrast, because in the moon, A lot of the contrast is very delicate color contrast, so I want to be sure that we understand that. And so for that region, I also focus up on this little crater right up here called Archimedes. And I chose Archimedes because the region around it is in one of these mare. It's very flat around it, but there's some subtle differences in color. So I've got one that's pretty corrugated and one that's pretty flat. So you'll see blow-ups of this as we kind of go through the processing. Now, when we talk about image processing in the society, we have a lot of people who focus on deep sky imaging, and we have people who focus on planetary imaging. And these two are very different regimes of operating, both in terms of how you take the images, but also how you process them after the fact. In particular, with deep sky imaging, that is things that are very dark and often extended, like nebulas and galaxies, you're really focusing on very few photons. You're using cooled cameras, large format, lots of pixels. They have slow frame rates, but you're usually taking acquisitions of maybe minutes easily, so that's really not important. You might be taking a couple hundred frames, and the software does alignment of images. Again, you take multiple images, but the software images that aligns them based on the positions of stars, right? So you have lots of stars here. And you use software like PixInsight or Cyril. For planetary imaging, because of the fact you've got this atmospheric turbulence that you're trying to beat, you usually want faster frame rates. And so the cameras are usually smaller. They usually have a smaller number of pixels, but they have faster frame rates. And usually what you end up doing is taking many, many frames, maybe 100 or up to 10,000 frames. And you're imaging, now you have to align those images, and we'll see that's a challenge. You don't have stars, right? If you're looking at the moon, you're operating under conditions of imaging where you're taking exposures of maybe a millisecond. And under those conditions, you don't see any stars. So the alignment of the images ends up being based on the planet boundaries and the features that are on those. And you use software like AutoStackered or Planetary System Stacker. AutoStackered is by far the most common. What I'm aiming for is the best of both worlds, right? I want a really high resolution image like you would get from this kind of camera, but I want to use it on planetary and solar so that I get the high resolution and the high frame rate or general resolution. So you can see already that's going to maybe be a little bit challenging. Okay, when I think about what is it that controls the resolution of the images that we take, there's two things we worry about. One is the laws of physics, and the laws of physics say that if I have 2 point objects and I image them through any kind of optical system, they don't image to a point. They image to something that is kind of Gaussian in shape, okay? It's called an airy disk. But that's one of the fundamental limits to resolution. And the second one is a practical one, which is the fact that we're sitting here on the ground. Every photon that comes to us from these extended objects comes through the atmosphere, and the atmosphere has turbulence. Especially here in the Midwest, we've got the jet stream over us. That jet stream has variations in density of the air. Those variations in density act like little tiny lenses. And depending on exactly where you are, those lenses focus light in different ways, and they shimmy back and forth. So it's like having a bunch of tiny little time-dependent lenses that are moving your image around, right? So we have to worry about both of those things. The key to doing the fast imaging, the so-called lucky imaging, is to look for these momentary periods in time and space when this shimmying is minimal, right? But it's never absent, and so we have to worry about that. All right, so let's talk about how those two actually work together. So first off, the laws of diffraction, or the laws of physics, basically say that we can predict what is the fundamental limit on our ability to image things that have a certain size. And in particular, if we have, for example, 2 point objects, like one green and one blue over here, they focus through our optical system onto these 2 little airy disks that are separated by a small amount. And there's a number of ways of defining the resolution of an optical system, but one of the common ones that people use is called Dawes limit. Dawes limit basically says that the best angular resolution, that is when this light from these 2 extended objects comes over and hits my lens of my objective, my telescope, and that bends the light down, and these 2 objects come through at slightly different angles. Now, what's not obvious is this angle is the same as, or the change separation in this angle is the same as the separation in that angle. And they focus at different points on my detector. And the difference in angular resolution is given by Dawes' so-called limit, 4.56, which has buried in it like the wavelength of light and a few other things, divided by the diameter of my objective in inches. Okay, so that's going to tell us how good of a resolution can we get in terms of discriminating between small things over here based on the objective size of my telescope, which is 120 millimeters. Now what we actually care about is how far is that on the detector. So if we know the angle, if we know how far apart those are in angle, delta r, we can just multiply that by the focal length of my telescope, f, and that gets us how far apart are these two little objects going to be on my sensor element. Okay? And what this says is that the laws of physics basically say that the smallest two objects that my telescope is able to discriminate using a 120 millimeter objective lens is going to produce two objects that are separated by 6.3 microns on my CCD detector. Okay, that's Dawes' limit. Now what matters is how does this match onto my CCD? So my CCD has a certain pixel size. My ASI 6200 has a pixel size of 3.56 microns. What I bring up is if you talk about this kind of high-resolution imaging, people talk a lot about sampling and what's called critical sampling, oversampling, and undersampling. Critical sampling means that the best resolution that the laws of physics say that I can get, that is the separation between, the minimum separation between two objects that I can resolve, is exactly equal to the distance between my pixels. So that's kind of a convenient critical point. If I have a CCD with smaller pixels like I do, right, my pixels are about half the size of that separation, this is what's called oversampling. So I'm sampling, I'm measuring at a finer resolution than the laws of physics say is my limit. You can also be undersampled, and people who do deep sky imaging are often undersampled. You have a rich field scope, you are undersampling because what you're trying to do is collect as many photons. And if you're photon starved, you usually want to be undersampled. If you want the highest resolution, you usually want to be critically sampled or a little bit oversampled. When you go into this oversampled regime, you don't really gain a lot by having these higher density pixels because you're already kind of at the resolution limits dictated by physics at the critical sampling point. But as I'll show you, there are some improvements in imaging that actually make it worthwhile. So for planetary and lunar imaging, people typically oversample by about a factor of 2. Right? You lose a little bit of light, but they're bright objects, so it doesn't really matter. You wouldn't want to do that, say, with a deep sky object. Okay? So that's kind of where we're at in terms of sampling. So I am oversampled by about a factor of 2, so I'm over here. Now I'm going to talk today a little bit about some of the software that I have been using to analyze what happens and understand how to align images better. I've done a lot of work recently in a language called Python. Does anybody else here use Python? Okay, we've got a few people who use
Photography.
Sorry? Okay, but anyway, so I've been doing like simulations and doing a lot of image processing using this language called Python. So I wrote a little Python simulation. What I did was I went onto the NASA site and downloaded a really high resolution image of the moon. And I wanted to say, well, how does my sampling affect what I'm going to see? So what I did first of all was I wrote a program that would resample an image of the moon at the resolution that I would have on my CCD. And then I applied the laws of physics. I wrote a program that would simulate this diffraction effect in the airy disk to be able to say, like, what should I expect my image to look like in the best possible world? So here's an example of an undersampled image. This is this crater Clavius, right? Again, it's a big crater, and then it's got a bunch of little craterlets in it. And if I am undersampled, I'm going to see something which, doesn't look too bad here, but if I take a high-resolution look at this crater right here, I forgot if it's this crater or this crater, but you see like the pixelation, right? My pixels are too big, so I'm like not going to get really good high-resolution data. If I'm critically sampled, I get something that looks like this. It looks a lot better if I blow up I guess it's this crater right here. Well, but you can still see the pixelation, right? This is so-called critical sampling, where that fundamental resolution of what can I resolve according to the laws of physics is exactly matched to my pixel size. So that's not too bad, right? And then if I'm oversampled, I get something that looks like this. So that blockiness is a little bit fuzzed out. In other ways, you don't see too much difference. Okay, so this is kind of where we're going to be. And this kind of sets a limit now that I can compare my images with at the end of the process and say, how good am I doing compared with what the fundamental limits of physics say I should be at. All right, so then that's what I've done. All right, let's talk a little bit about the atmospheric turbulence. The turbulence is something that is a problem. We often call it the seeing. The seeing measured in arc seconds is a measure of how much is an image shimmying back and forth because of this atmospheric turbulence. Again, here in the jet stream, again, this is acting like a little lens. It's deviating the light that's coming from the moon to our lens, and that is resulting in shifting in the images. So now this is real data, and what I'm going to show you is high-resolution images, again, of Clavius, taken my telescope in the backyard, not NASA site. Taken at high resolution, and what I want you to see is if we look at multiple frames that we've acquired, what does it look like? Okay, so let's see, I think I might have to do this here. And I want you to do is look for two things. One is the image will shift back and forth, but also you'll see the image will kind of compress and expand in certain regions, and it will also come in and out of focus, which might be a little bit hard to see in the image of the moon. So this is just like a 10-second. Okay, so that's, that's what you're dealing with. Okay, so it's coming in and out of focus, expanding, contracting. And over on the right, I have a similar image of the sun. So this is just a continuum image of that little sunspot region I showed you before. I want to point out right away that what I'm interested in is not so much the sunspots, but I want to capture that very fine granulation. So if you look over here, for example, you can see this fine granulation of the sun, and you see that some regions are very fuzzy, like this region right here appears to be fuzzy. This region appears to be sharp. And if we look at what happens as we go through a little movie, right, you'll see that frame by frame, different parts of this image are coming in and out of focus. It is also expanding, contracting, and it is distorting. Right? So it's really important that the image is not just shifting back and forth, but also this idea of the lucky imaging. We have to identify not only what is the best frame, but we have to identify what is the best part of every frame in order to come up ultimately with the best image. Okay, so that's what we're going to end up wanting to do. All right, so I'm going to take some data, right? So I'm not going to take tens of thousands of frames. I'm going to take a few hundred frames. I'll take 60 frames of red, 60 frames of green, 60 frames of blue. That's already almost 200 frames at 100 and some megabytes each, so it's like 20 gigabytes of data. And I'm going to repeat that a couple times just to be sure, each time like adjusting the focus a little bit in between. Okay, so if you've done this kind of imaging before, you know that the most common program to use for planetary and lunar images is a program called AutoStacker. It does everything we want it to do. When you are using a normal, I'll say normal, 1,000 by 1,000, maybe 8 or 12-bit camera. If I try it with the images that I'm doing, which are 16-bit, really large, crashed. Okay. Well, I thought, okay, AutoStacker's crashing. Let's go over to Registrax. Okay, put him into Registrax.
Even worse.
It crashes. Okay. There's a Python-based program called Planetary System Stacker, and I thought, okay, let's try that. How many people think it crashes? Yes. Okay. So they say necessity is the mother of invention. Okay, so at this point I know, okay, I've got this background in image processing. I've learned a little bit of Python so far previous to this. But I've not done a lot of coding of Python to solve astro imaging. I've done some before, but not a lot. but kind of necessity kind of pushed me toward the limit of doing Python. So pretty much everything I'm doing here is with Python. Okay, so I just want to talk about Python for people who haven't used it, because when I started the image processing back in 1985, I had to write my own programs in Fortran. And they would be, you know, tens or hundreds of lines of code, and it was, you know, everything had to be done from defining arrays and everything. The world has changed completely, and it's one of the really big advantages of Python. It has a lot of advantages. I'm a big fan of it, but it's really flexible. It's easy to learn. Any of your children or grandchildren who have ever done anything in the field of robotics will know Python. All right. It's a friendly, easy to use language. But the best part about it is everything is open source, and there's an enormous user base of people who share programs. And there's lots of add-ons for doing specialized kinds of things. So for example, for doing numerical processing, there's something called NumPy. For doing image processing, there's scikit imaging that does imaging or alignment of images by various methods. There's an astronomy-focused toolkit called Astropy, which is nice because it has one-line commands for reading FITS files and writing FITS files. All right? And then I actually, actually Astropy has tons of stuff in it. I just have the tip of the iceberg. I'm going to show you some image alignment done by a different method that I discovered using something called DIPy, diffusion imaging in Python, which is actually a package developed from the medical community for aligning brain images. Okay, but anyway, the point is there's lots of toolkits out there that you can use. But the big advantage of it is that you don't have to write lots of code. You can take advantage of the fact that people have written very, very well documented software, and you can simply import it like a one-line command, not like dragging in thousands of lines of code into your programs. So now again, I'm not going to show you lots of code, right? But I just want to point out like everything to do alignment of images using this diffusion method is about 15 lines of code. Okay? It's 2 lines of code to read in a FITS file. It's 3 lines of code to register statically 2 images. It's another 4 lines to let them warp to the store. And it's 1 more line of code to write out the image. Right? This is not hundreds of lines of code. This is taking advantage of the fact that there's lots of smart people who have spent a lot of time developing programs, code, that you can simply import. And that's the big difference from 40 years ago and now, is the reusability and portability, and the fact that Python is basically like it's an integrator that allows you to integrate code from many different sources. And all these things work together. So I talked about like the NumPy toolkit and the SciPy toolkit and the Astropy toolkit. You can have all of these working at the same time in your program. They don't conflict. In fact, it's specifically designed so that the various dependencies and conflicts are resolved very early on in the process. Okay, so that's the only code I'm going to show. You're going to see more Python in the next 20 minutes or so. The other tool I just want to mention is ImageJ. ImageJ has been around for like 20 years. It was developed by the National Institute of Health, NIH, for analyzing images primarily in the medical field. So it's a little bit dated. There's a recent release of a program called Fiji that is supposed to be an updated version of it. I've not used Fiji, but I want to show you just a little bit about ImageJ. I'm going to pop out of my thing here, and I'm just going to show you, because one of the things I don't see very many people do is treating images as data. So what I like about ImageJ, it's a really light program. If you want to open a TIFF file or a FITS file, it opens in like a second. It's not like trying to open it in PixInsight where it loads 20 gigabytes of stuff to open up a file and let you look at it. It's very fast, but it also lets you do some things that you can't do that as a scientist I find incredibly useful. So I'm going to just open up. This is one frame of a solar image, okay? So the questions sometimes you want to ask are like, I don't want to look at this image necessarily as if it's a top-down image. I want to know, like, how dark is a sunspot compared with the region surrounding it. So for example, you can very easily say draw a line. Draw the line tool, and I'm going to draw a line going over there. And now I can simply go to analyze and plot profile. And now I can see, like, okay, how dark is a sunspot quantitatively, right? It's 25,000 pixels over most of the sun. It drops down to 5,000 pixels, right? You can see the difference between the umbra, the darkest part, and the penumbra, right? The region surrounding it, right? You can see right there. You can go into a live mode. And I'm going to move this over. And now I can just sit here and draw any image, any line that I want, and it's going to show me what's happening along that image. If I want to write out that data, I can go over here and just write out that data in like a CSV file or something you can read into Excel or whatever is a plotting program. So that's one of the really nice things about it. Another nice thing is you can say draw a, let's say I want to draw a square and say I want to understand like what's a histogram of this region look like. I'm going to close this for a second. And I can go up here to measure. Oops, sorry, that's not where I want it to be. Measure is going to give me like how many pixels and what's the mean and the average. I don't want to save that, but I can do, where'd it go? Man, this one I'm going to do, I can't see it now. It's a little hard with that light shining on me, actually, it's a little.
It's down a little bit.
About
Down.
three-fourths way down.
Three-quarters, yeah. Yeah, you just passed it.
Oh,
Yeah.
histogram.
Yeah.
Yeah, thank you. There's a histogram. You can have an area and it'll tell you the average and the mean and the mode, all the statistical information. You can also do a little three-dimensional plots, which is kind of fun. So you can go over here and say, instead of looking at this as a two-dimensional plot, I actually want to go to, there's two ways you can do this. Here's a three-dimensional plot. I'm going to do an interactive three-dimensional surface plot. I have to set the range for X, Y, and Z. Oops, sorry. Yeah, it's hard doing this in front of lots of people. If any of you looked in the Capital Skies newsletter, the first edition, and saw the little three-dimensional plots that I put there, right? That's how we did these, okay? So the interactive three-dimensional plot, and I'm sorry it's not showing up like well, but I'm just not able right now to get the range quite right very easily. But, okay, but nevertheless, like there's lots of stuff and it's free, right? It's a very free, lightweight, very easy to use program. Okay, so that's not, I'm gonna stop right there and go back to my main presentation, but I said that I would highlight, like, this is one of the most useful tools that I use on a daily basis. It's sitting right here in my bottom of my screen because I use it almost every day. And I thought people should know about it, especially given it's really, just really lightweight and free. Okay, so let's go back to the image processing, right? So what I want to do is replicate in Python what AutoStacker does. So there's three main things we need to be able to do. We need to be able to measure sharpness of images, so we know what frames and what parts of the frames are sharpest. We need to have a way of aligning them, not just shifting them, but also correcting for distortion, and that's shimmying back and forth. And then we need to figure out how are we going to actually stack them in such a way that we take the sharpest parts of each frame in order to get one really sharp frame at the end. Right? That's pretty much what I'm going to do. I don't use these in isolation, and one of the things I've learned is every program has its own purpose. So PixInsight, for example, is really good at doing image calibration. I don't need to replicate that. I could, but I don't need to. All I need to be able to do is have that write in a format that I can read. So PixInsight can read, and instead of writing in the XISF format, which is annoying, you can have it write out in fits. and everything can read this pretty much. Okay, so let's move on. All right, we're gonna get a little bit more under the hood right now, like how does an image actually measure sharpness, okay? A lot of the functions for imaging processing are based on a mathematical process called a convolution. Convolution can be used to measure sharpness, it can be used for edge detection, it can be used for filtering, to smooth images. There's lots of things that it can be done. And if you do any of these image processing, you are using convolutions under the hood, right? All right, so this is a little, like a geeky slide, okay? So maybe not for everybody, right? But, you know, I promise under the hood, how far under the hood do you want to get? That's kind of up to you. We'll come back. All right, but here's the basic idea of how AutoStacker and all these programs measure the sharpness of your image. Suppose I have an image, so here's that same little crater, and I want to measure the sharpness at a particular, oh, my pointer is, oh, sorry. My pointer is no longer, oh, there it is. I want to measure the sharpness at the green point, okay? So I've got a little region here, and I want to measure the sharpness at a particular point. Well, that image is really a matrix of numbers. And so I've got here, I want to measure the sharpness at this point represented by the little greenish square right here. There's other stuff around it, right? That's all the other stuff in this blue box. So this blue box here kind of represents the numbers would be here. So what I'm going to do is I'm going to take something called a kernel. So the kernel, with a K, not a C, is kind of the heart of what you do. Different kernels will do different things. This particular kernel here, 4 in the middle and -1 above and below, is a sharpening kernel. It's called the Laplacian. If I want to measure the sharpness, what this is essentially doing is taking the point that I'm at, and it's going to subtract the 4 adjacent points. So what I'm going to do is I'm going to take that kernel, and if I want to know what's the sharpness at the green point, I'm going to take that kernel, I'm going to plop it right down on front, on top. I'm going to multiply the black number and the red number in each square, and then I'm going to add them up. Okay? If the surface is flat, I have a 4 in the middle, 1, 1, 1, 1, I get 0. So a flat surface gives me 0. Something that's corrugated is going to give me either a positive or a negative number, depending on how corrugated it is. And I'm going to take the absolute value of that. And that's going to be my sharpness. Okay? As I've shown it, we just determined the sharpness at one point in the image. But I can take that kernel and I can put it on a different point and measure the sharpness somewhere else. And I can take that kernel and I can smush it over the entire image, each time doing the same thing. And then I actually get an image, a new image that I'm going to call a sharpness map. It is an image that tells me how sharp is the actual image at each point. So that's what a sharpness map looks like. Now, if I take all these numbers in the sharpness map and add them up, that's the sharpness of the image. So when you go into AutoStacker and it ranks the sharpness of your image, this is what it's doing, right? It's doing this for every single frame and then spitting out numbers and sorting them. Now, I think this is really cool. This is under hood that you don't see in any of the normal software. But I think it's really cool to look at, okay? So here's a regular image of the sun, and here's a sharpness map of the sun. And I mentioned before this idea that you can see like the shimmying back and forth and regions coming in and out of focus. Well, you can see this in the movie now, right? So here's the sunspots. They end up with a ring at the boundary between the umbra and another ring at the boundary of the penumbra. But you see like the region where the fine granulation is, you see regions where it's sharp, regions where it's not sharp, and from frame by frame, you see this kind of, right? So every single image has regions that are bright and some that are dark. The regions that are bright are regions where the real image is sharp, and regions that are dark are places where the real image is dull. I just thought this was really cool, okay? And what I thought was cool about it is you actually see like bands going across in this direction. If you look, Like, it's not totally random. You see kind of bands going, whoops, going across. Let me just go back again. And, doggone it. Sorry. I think that those bands are like the jet stream. To me, they kind of go from upper left to lower right on average. Maybe, maybe I'm making it up, right? I don't know. But in any case, I thought that was kind of cool that you can really like visualize something that, you don't see in AutoStacker. It does this, but it never shows the result. You can look at the same thing on the moon. The moon looks pretty funky when you look at the sharpness map, and it's a little harder to see the same thing because on average, the moon has a lot more corrugation than the sun does. But again, you see this kind of banding, right, of parts of the image that are frames that are sharp in some parts and sharp that are not. Now, I mentioned that the kernel kind of is what kind of determines how you measure sharpness. There's lots of different kernels. You can take, instead of taking a 3x3, you can take a 5x5 area, or 9x9, or 11x11. It's almost always an odd number. There's other variations on that. So there's different ways of measuring sharpness. And actually, I went through and I looked at about 5 different methods of measuring sharpness because I wanted to say, well, do they give the same result? Okay? And the answer is, sort of, okay? But not always. So this is a weird plot, but what I did was I measured the sharpness using several different kernels. I compared that with what AutoStacker gave as the ranking of sharpness of a bunch of images. And I thought it was interesting that these programs generally agree on what are the very sharpest images. I'm sorry, so this is the rank order. I measured 250 images by more than one method and said, point down here says, which image does this method called FFT tell me is the sharpest image? That's number 1. FFT's least sharp image is 250. So something that is the same when measured by both methods will fall on a line. Something that falls off the line says, one method is telling me it's sharp, another method is telling me it's dull. Okay? And what's interesting is the different methods they more or less agree on what are the sharpest images, like the first 10 or so, and they agree on what are the worst images. But in the middle, one program says, well, this is the fifth, like this little dot right here. It's like 51 on the vertical scale. Tell me it's the 51st sharpest image, but this program is telling me it's like the 30th. Okay? So there's just a lot of variation. So you're thinking, I've gone through all this work. I really want to have the ordering of these images right. Well, there is no right order. And the reason is, again, the sharpness varies all over the map on this image. So depending on the details of how you measure sharpness, you get slightly different results. But on average, they're pretty good. Okay, so that's measuring image sharpness. The next thing we want to do is say, how are we going to align the images? And this actually is, I think, where the problem comes in terms of doing really high resolution imaging, is the way that programs like AutoStacker and Registax and Planetary System Stacker is the way that they register and align images is using something called feature points. So you go in the program and you load in your image and it identifies a whole bunch of points, right? The way the program works is it identifies these things called feature points. And a feature point, by definition, is a corner. And this is the weak point. The programs are defining what is a feature point by looking for corners. Things where there's a sudden sharp change in the vertical direction and in the horizontal direction that form a corner to make an alignment point. Because from such a structure, it can tell which way does it need to shimmy the image in order to get it to align. And the challenge number 1 is round things don't have corners, right? But for example, if you ever used AutoStacker or Registack, they tell you specifically, don't put the alignment points near the edge of the disk, right? And that's because that's like the worst possible place is near something that's round. Okay? But the challenge is it doesn't do very well on round images. It doesn't do very well in low contrast images, low contrast regions like the middle of this crater. Okay, so I've not done this, but I just want to point out to you, again, that I just loaded one of my images into Registax to say, well, where would it find the alignment points? And you can see the red dots here are the alignment points that it finds, and then it defines a little neighborhood around them. But there's regions like this region where there's no alignment points. Well, if there's no alignment points, it's not going to align the images, right? Okay, that's kind of a fundamental problem. And it's got like 2,000 points, okay, but 2,000 point in a 125 megabyte image is still a small fraction of the image that is actually getting registered, right? These programs are not registering your image. They are registering the alignment points that it has chosen within the image, okay? And that's a bit of a problem. So I instead have gone to this, so I searched and searched and searched for what else is available, and I consistently came across this idea of using something called whole image warping. And the program that I came across doing this is in this DIPy, Diffusion Imaging for Python package, that was developed for overlaying different kinds of brain images, like an MRI image and a CAT scan, right? Sometimes they're three-dimensional images, so actually they have provision and they're for actually aligning in 3 dimensions. But the important point is people have put a ton of effort into doing this because of the importance in biomedical imaging. A lot of money has gone into this, a lot of optimization, and it's there for free, right? So why not? If it can align brain images, it can align moon images, right? Okay, so what's different about this is the idea of how does it warp the image? Is instead of having alignment points and trying to move the alignment points back and forth, it actually using something called a cross correlation. Okay, this is another geeky point, right? But I figure, well, why not? Cross correlation. How do we know when 2 objects are aligned? Well, the very simple example is up on top. How do we know when a yellow circle and a blue something or other are aligned? Well, you kind of intuitively know that where these 2 are overlapped, it's green, or at least sort of green, right? And then if I wanted to say when 2 slightly different objects are maximally aligned, it would be when the area of the green part is largest, right? So these are not aligned, these are not aligned, but this is aligned. So mathematically, how do we do that? Mathematically, we recognize that this yellow object and blue object are numbers in an array. Okay, here's one array for the yellow object. I've put in like half at the edges, and 0 outside, but 1 in the middle. Same thing for the blue thing. And we do very much like we did for the convolution. I'm not going to show it, but you take the blue thing, you plop it down on top of the yellow thing, you multiply all of those individual little elements, and you add them up. Now it should be kind of obvious that that's going to be maximal when the 1s are overlapped with other 1s, and not when 1s are overlapped with 0s, right? The important point about the cross correlation is that it's using all the data, right? It's not just aligning based on alignment points, but it's actually aligning based on the entire image, okay? Now again, I pointed out that when we think about doing these very complicated image processing functions, that 40 years ago, you'd write thousands of lines of computer code. Somebody's already done that, right? I only have to write 8 lines of computer code in Python in order to do this. 2 to read in the image, 2 or 3 to align them statically, and 3 more to let them warp, right? That's it. It's not that complicated. Well, how well does it do? Well, here's that crater again. Whoops. Here's the crater before. Right? You see it's jumping around and expanding, contracting, and doing all the things that you see that the crater does. And here's the same crater afterwards. Right? So, you see that it's still coming in and out of focus a little bit, right? Because we're not changing the focus. But there's no longer that shimming and expansion and other things. And the entire image, right, is done this way. So it turns out to be a really nice way of doing the alignment. Right, so that works because it's really good alignment. The third thing we need to do is stack the images. So now we've got a bunch of images, they're all beautifully aligned. So the structures, if you think about these images as being like a stack, they're all on top of one another. What I need to do now is pick out the sharpest parts of the sharpest images and take those together in order to make an image. This was the longest program actually that I had to write. So how do we do this? We have a sharpness map. I showed you what a sharpness map looked like, right? Some areas where it's white, the value is big, those are regions that are sharp. I've represented those in green. In some image, say one frame, I'll have some pixels that are sharp, represented by green, and some that are dull, represented by red. I'll have another frame where maybe they're both somewhere intermediate, and then I'll have another frame where maybe it's kind of reversed. The region that was dull here is now sharp, and the region that was sharp is now kind of right? Okay. I also have my image. This is kind of my image, right? Here's the sharp region, right? It has lots of structure, intermediate image, right? Here I have this region that in the sharpness map tells me my image is dull. Here it's sharp. I get a sharp boundary between the black region and the other. What I want to do is find a way, I want to have this part of this frame combined with this part of this frame. So I have the sharpest part of each individual frame of this 250 frame stack. Okay, so how do I do that? Well, if I have a number that tells me how sharp the image is, I can tell what's the sharpest frame. So if I look at this given pixel, I can say, well, frame 1 is the sharpest frame at this pixel. Frame 3 is the sharpest at this pixel. So it's number 1, this is the sharpest frame, this is the second sharpest frame, this is the dullest frame, if I only have 3 frames. Okay, so I've got a rank ordering. Now what I want to do is define how many of these do I want to add together, so I'm going to assign a weight. So I'm going to assign the sharpest frame, for example, I might assign a weight of 1/2, just arbitrary. I might assign a weight of 0.3 to the second sharpest and 0.2 to the least sharp. These add up to 1, 0.5 plus 0.3 plus 0.2 is 1. That's important, okay? But now what I do is I take 0.5 times the value of my image frame here, 0.2 times that one, 0.3 times that one, and that gives me a weighted stack, okay, in which I now have these weighted image frames, and now I just add them up. And I get my final stacked image. I do that for the red images, I do it for the green images, and I get the blue images, and now I've got a stack of sharp, really well-defined RGB. Then I can use anything to combine them. I can use Photoshop, I can do anything. Right, so that's what I did, okay? That turns out to work. Now again, how close is the result to the best we can expect? So here again is that image taken from the NASA database. Here it is after I convolute in that physics. Here's what it is after I smooth it by a factor of 2 to make it the same pixel density as my actual image. And here's my actual image, right? Now, the sun is at a different location. You could look at this crater and you see that it's light over here, and this crater, and it's dark in the same region over. It's almost like everything's reversed, right? Because the sun's on the opposite side. But, you can pretty much see, I think, that even at the level of detail of 1 pixel, that the regions, the structures that are present here are also present over here, maybe with an inverted contrast because of that difference in so maybe this is even a little sharper, okay?
Yeah, I think
Well,
so.
I mean, it turns out that you can, in fact, get slightly sharper than the Dawes limit when you do this kind of recombination process. I won't go into, can't do a lot better, but you could do a little bit better. That's like drizzling, kind of gets fine. Okay, so anyway, what that gets you then are, oh, that's weird, are images like this. So this was the one that I did for John for the first quarter image, the third quarter image, and those are over here. You can do the same thing with the solar image, but anyway, that's kind of my journey in Python processing for image processing. If there are other people who are interested in Python for this kind of astrophotography stuff, I was thinking we might want to actually form a little subgroup of some kind. If people are interested, I'd be very open to that. I'm not an expert programmer. I am a hacker. If you saw my code, it's really ugly. Okay? It's made so that I can read it, nobody else. But anyway, with that, I'll just thank you and happy to take any questions.
If anyone has questions, just raise your hand and I'll bring the microphone to you.
I'm just curious, how new is your computer? You said 30-minute processing time. How old is your computer?
Talk to my wife.
Which
She's right.
computer?
Well,
Which of the five?
okay, so I was doing these, actually, I acquire my data on a little Nook, a next unit of computing, that's on the bottom of my little trolley, right? So on that, the image registration part is the slowest step. And that takes about half an hour per image on that. I recently set up a new computer with an AMD processor and 64 gigabytes of memory. The AMD processor has 24 cores, and the Python program can, like, if you're stacking images, that can be done in parallel. So with that, it's still slow, you know, but we got all winter. So what's your hurry? Yeah, it is much, much slower. Like, you don't do things in real time.
Which AMD?
I don't remember, but I mean, I've done it on a laptop, right? I did that, the moon image on the metal, I did that on a laptop, right? It's slow, right? It might take overnight, but.
I was wondering if instead of ranking sharpness, you multiplied each image by its sharpness image and add them all up, add up all the sharpness images, and then divide by that to normalize the image.
Yeah, I thought about doing that. And what I was a little bit worried about was noise amplification, that if you have noise in the image, it's more likely to come in that way. I mean, I kind of thought about that. I mean, that would be interesting to try, right? If you want to try it, right? Or maybe I will try it.
I think it might work.
Yeah, I mean, actually what I do right now is I rank order the images and then I scale them based on an exponential fall off. And I just choose what is the exponential fall off. There's probably some AI way of determining like what's the best number of frames to stack, but I haven't, but actually that's kind of the next thing is like, how many frames do you stack is kind of arbitrary and people simply, in AutoStacker, people simply do it and then they look at the result. But I think there's probably a better way of doing that too, like based on analysis of the noise. But yeah, I mean, that's a perfectly viable way of doing it too. Maybe I'll do it and show you what the result looks like.
I'd be curious.
Yeah, okay.
I do a lot of image stacking in microscopy using an optical compound type of microscope.
Mhm.
And I was wondering if there's any application to this type of thing as I scan 1 micron at a time through this, so like a vertical slice of the image. Is there any application for this to try to, if I used a video camera as the process was taking place, as a stage was going up and down, whether this could be used to sharpen those images?
Probably, yeah. I mean, this is essentially what DIPAR, right? I mean, this three-dimensional brain imaging is basically like a confocal microscope taking a through focus series is very much like what they're doing with the brain imaging. So yeah, I mean, the program should be transparent in terms of like what the nature of the data are. So,
I think Carol had a question, right with you.
Carol and Dan had a question too.
Oh, yeah.
What does the wavelets do in AutoStacker? How is that sharpening?
Yeah.
It's magic, but I don't know what it's
Okay.
doing.
So wavelets are, okay, so let me take a step back. A Fourier transform takes an image and tries to represent it as a series of sines and cosines of different frequencies, okay? Low frequency, high frequency. A wavelet is kind of a structure like that is designed to provide more localized sharpening. It's a little bit hard to explain. For example, JPEG compression works by taking an image, and then it takes the difference between alternating pixels. And that looks at the finer gradation structure, and then it does that again and looks at the finer gradations. So it is a way of defining, what's the right word? It's a way of localizing the idea of how sharp is an image on a particular length scale. There's actually different kinds of wavelets, and they actually don't tell you anything about that. So that's kind of about the limit of what I know.
And some are more coarse than others, aren't they? Some wavelet sliders in AutoStacker are more coarse sharpening.
They're basically looking at structures on powers of 2. So every time you go from one wavelet to the next wavelet to the next wavelet, you're changing the length scale of sharpening by a factor of 2. Okay? The details of how that's done mathematically depend on the kind of wavelet that's used, and there's many different kinds of wavelets, and I don't know any more than that. That's kind of...
I think, for if you do a Fourier transform, the basis functions are infinitely long
Yeah.
sine waves. For wavelets, you're compressing. You're not having infinitely long basis functions, so that the function is smaller. And so it's more localized, as you were saying.
Right, yeah, but the shape of it...
And the shape of it, lots of different ways you could do it.
Right.
Was there someone else?
Yeah.
Dan, do you have a question?
Yeah, so initially you had decided, based on the resolution of the final image you wanted, that you were gonna oversample by about a factor of 2.
Yep.
And you started taking those pictures and you fed them into the existing software and had them all crash. Was there a moment where you said, I could write my own software for this, or I could just reduce these file sizes by not oversampling, by binning this sensor and going from, you know, a 100 megabit file to, I don't know, would that be a 25 megabyte file then for each of these? And then maybe one of these softwares would work. What was going through your mind at this point?
Okay, yeah, what was going through my mind is the following. When people talk about the resolution limit of the system, right, like Dawes limit, that is not a hard limit, right? When you can have two objects that are separated by something smaller than the Dawes limit, and they will result in a little depression, right? So you're losing, you know, you're
losing
getting,
some data, but not all of it.
right, that's right, but you are losing some data. And my goal was to say, like, doggone it, I don't want to throw away anything, right? I mean, it's kind of like people try to recover that by drizzling,
Yeah.
right? Right? But drizzling only works if you are intrinsically undersampled. If you are not undersampled, is that mine?
You might want it, the pointer, if you're done with your pointer, you might want to put that down.
There we go. Good idea. If you're not undersampled, then drizzling doesn't work. So anyway, I wanted to explore the limit, right? What was the very best that I could do? And I just, doggone it, I don't want to throw away, and that's the same mindset as, I don't care if it takes 2 days. In fact, in the early implementation of the program, it did take me a couple of days to run through these, because, you know, I'm not a software guru.
How long did it take you to research all of these Python libraries that exist? Decide, you know, vet them, which ones are gonna work for you,
You know,
which
in the
ones...
end, I don't know this is the best one. I know that it's one that works.
The one that work, well, that's what I mean, but when I do a, you know, some sort of project like this, you know, that's 3 times the amount of time than actually doing it is researching what,
Oh, absolutely.
yeah.
Absolutely. You know, as a scientist, to me, the journey.
That's the fun of it.
The journey is the fun of it. So that research and say, hey, I've got something that works better than AutoStacker, you know. To me, that's satisfying and rewarding. So it did take time, right? But it was maybe like a month or 2, right? And then since then, I've done a lot of improvements. Like I found there was a bug in my stacking software that I only found when I was preparing for this talk. So I'm glad I did this talk because I found the bug. But yeah.
Thank you for such a rich talk. I was struck by the videos of your, I've forgotten the adjective anyway,
Sharpness
but
maps?
the sharpness maps.
Yeah.
And the anisotropic features that you were reading in as possibly the jet stream. The next iteration may have to be AI. I can't see how to do this in Python, but trying to figure out which parts of the anisotropic jet stream-like features are the clearer parts and which are less so. And can you start seeing those patterns that you were detecting to anticipate so that you then actually weight more heavily the clearer images when the jet stream is dormant there, and do away with the others. And that way what you're doing is integrating the best images without the warpage.
Yeah, that's a lot
A
like
lot of
what's done
work.
in solar imaging, right? You know, like a seeing-based trigger, right? Where people do solar, right? That's a common thing. That's a good point. You could probably like imagine focusing the limb of the moon onto some detector element and looking for how much is it shimmying, and when it's shimmying less, trigger it to start taking data, which is kind of like what solar seeing-based detection does.
On that topic, you may want to look at another feature in Python, which is Raison, which is predictive analytics. And,
there's a whole lot of AI stuff in there.
Right,
I haven't
exactly. And you could be applying some of the Python predictive analytics to it too.
Okay, I'll think about that, yeah.
All right, one more question. I think we have time for one or two more questions.
Yeah, could you go back to the slide where you were showing how you did the stacking?
Yep.
Yeah, that one.
Yep.
So, I'm sorry.
You don't have to hold it real close.
So what exactly, once again, was the mathematical procedure you used for that?
So I measure the sharpness,
Right.
right? Green
Yep.
is high sharpness, red is low sharpness, and I rank order them,
Yep,
all the different frames, 1 up through 250.
okay.
And then I decided that I wanted to weight, on average, say the first 3 frames. Again, you could choose that any way you want, right? But I said, I'm gonna make my stack from the 3 sharpest. I'm gonna choose, at each pixel, I'm going to choose the 3 sharpest frames, whatever they happen to be, out of the 250 frames. And whatever is that sharpest frame for that pixel, I'm gonna weight that 50%, and I'm gonna weight the next one 30%, and then 20%. So I go from the rank ordering to a weighting factor, right, that corresponds to how heavily I want to weight each respective image. And then I simply multiply them. So I take, if this matrix now is how heavily I'm going to weight each pixel in each image. By the way, this creates like 250 more files that I actually write out on disk, and then I read them back in, just for memory's sake. But then I just take half, multiply it. If this frame, this pixel, has a weight of a half, I just multiply the value of the actual image in that frame, put that into a new image, and then I just stack them down.
Okay, cool.
Yeah.
Thank you.
So you're stacking individual pixels, you're not actually stacking frames.
Yeah, actually, I cheated a little bit. In the sharpness map, I'm actually taking a little region that's like 11 pixels by 11 pixels. Because when you look at that sharpness map, you get an idea of what's the length scale over which the sharpness is actually varying. And on the length scale of like 11 pixels, things are pretty constant. So that makes these images much smaller.
So there's essentially a grain size to this
Yeah.
seeing effect.
Yeah, well, actually, I take 11 by 11, and then I have them overlapping by a couple pixels, just to be sure there's no like sharp boundaries, so it kind of smoothly transgoes from one. Yeah.
All right, one more question.
First, I just want to tell you, this was a fantastically interesting talk. It was really great. And you were talking about the jet stream.
Yeah.
I think my eye picked it up as being diagonal, but
Yeah.
there's a convolution for that too. Or you can do fast forward transform, and it would tell you if
Yeah.
there was a directionality.
That's true, you're right, absolutely.
This is,
There's a lot of stuff you can do, like, well, I mean, this is the point, right? Once you get under the hood and you can see what's going on, there's a lot more information there than you get than just a picture of the other end.
this is a backdoor project here. You're gonna model wind shear eddies of the jet stream by taking
Maybe,
pictures of the moon.
and I'll feed the information to you, so when you're
Exactly.
taking off and you're playing with your family, you'll like be safe.
All you need is a good background flat like the sun to,
Exactly.
that's the trick, is having the background to be able to show where all that turbulence is at.
Yeah.
How fascinating. Well, this has been really, I guess I'll never look at stacking the same. Especially if you can pick out pixels and stack, from different pictures,
Yeah.
subframes, and then.
This is essentially what
create a whole new
AutoStacker
stack
does. I
down.
didn't invent this, right? I mean, if you look at AutoStacker or any of the stacking programs, I think they do exactly the same thing, right?
Yeah.
They just don't really tell you what they're doing.
Very fascinating.
I'm happy to stick around and talk.
Yeah, stick around to answer. We're gonna close up the room by 9 o'clock, but stick around to ask Bob more questions. And remember, we'll be right back here for the next Madison Astronomical Society meeting on February 14th. We look forward to seeing you then. And thank you for being here tonight, and we'll see you all soon, everyone. Good night.